Well, let's look at how we do find the slope of a tangent to a curve in more detail. So remember we said that when it comes to measuring the slope of a curve, it's actually the tangent slope that we were interested in. So here's just some random curve, y equals function x. And if we wanted to find the gradient function at p there. So there's the tangent. It would be the slope of the tangent, which I've labelled k, at that point. I could estimate it. This time I'm going to use p as one of the points of my estimate, and I'll have the other point as q. So pq would be an estimate. Not a great estimate, the way it looks at the moment, but of course I could make it a better one by moving the position of q. And so the question is, well, where should we move q to get our best possible estimate? And I guess the answer is, well, if you moved q so that it was sitting on top of p, then you would get the perfect answer. Of course, we can't do that. We can move it as close as possible. And this is where the idea of limits is going to come on. Because what we're interested in is, as the distance between them gets closer and closer to 0, what is this value going to be? Because that will be the answer. So I'll just expand that out a bit there. So there's p and q. So p will have coordinates of x and a function value of function x. Q, I've added a little bit on, so I've added h on, and its function value therefore is function x plus h. So the slope of pq will end up being function x plus h minus function x, but then the bottom of the fraction we get some cancelling, and we end up with h. So to get that exact value, we want the limit as h gets closer and closer to 0. Now obviously h can't equal 0 because we'll end up with 0 on the bottom of the fraction. So the slope of the tangent, the exact slope of the tangent, will be whatever that limit turns out to be. That is the derivative of y with respect to x. So how does y change, or how does the function value change as x changes? Different symbols for the derivative. Probably the most common one we use is dy dx. And that comes from, I guess, the d from delta. Delta is often used for change. And so that's how we end up with the d there. Y with just a dash, or I think they call those prime is the technical name for them, so y prime. F dash x. Sometimes we just say, actually write the function in instead of y. And we say, okay, I'm going to differentiate this function with respect to x. But at the end of the day, our derivative is a rate of change, how something is changing. And okay, we're talking about it with the graph of whatever's happening, and so it's the change in the function value. But of course, the graph could be representing anything. It could be displacement versus time. So it could be saying, well, as time changes, how does the displacement change? Or could be anything, really. So thus, we get our formula for the derivative. Now, you remember we worked out one for straight lines before. That was easy. We came up with a semicircle one. That wasn't as easy, but we got a formula for it. But then at that point we were saying, well, we need to estimate based on secants. Well, now we can use this to not estimate but get an exact answer. This is what's known as differentiating from first principles, bringing it all back to scratch and starting from scratch. So if I had to differentiate y equals 6x plus 1, now I've deliberately chosen a straight line here because we know what this derivative should be. We said it was going to be that constant value of 6 in this case, the slope of the line. Well, function x would be 6x plus 1. Function x plus h then would be 6x plus 6h plus 1. There's our formula. Limit as h approaches 0, function x plus h minus function x all over h. So if I sub in, I get some cancelling that will happen in the numerator there. The 6x's are going to subtract, and the 1's will subtract, and I just get 6h on h. And this becomes one of those limits that we were looking at yesterday where, hang on, 0 and 0, that doesn't make sense. But we can cancel in this case with the h's, and we end up with a constant 6. So we're saying h approaches 0, it really doesn't matter what h is in this case. we'll get an answer of 6, and that is what we were expecting. So let's try it with a parabola then, because that was one of the ones where we couldn't just come up with a nice neat formula before. So x squared minus 5x plus 2, we're going to find the equation of the tangent at the particular point 1, negative 2. Well, a tangent's a line. If I want to find the equation of a line, I need a point. I've got that. But I also need to know the slope, or the gradient. So I need to work out the derivative, or gradient function, the function that will tell us the gradient. Function x squared minus 5x plus 2. Function x plus h is x plus h squared minus 5x plus h plus 2. Expand that out, nothing tidies up there. Let's sub it into our formula. Whoa, but we do get a lot of cancelling here. We've got x squared minus x squared, so that goes away. Xh is no, h squared's no. Minus 5x plus 5x, that'll cancel. And then the 2 and the minus 2. And if you notice, now we can cancel the h into everything. There's a common factor of h on the top. So we end up with 2x plus h minus 5. We want to know as h approaches 0. But now this is a limit where I can just do a direct substitution. And so we come up with the formula 2x minus 5. Remember, 2x minus 5 is not the slope. That's the gradient function. So that's the function that will find the slope for us. We want at the point 1, negative 2. So when x equals 1, that derivative turns out to be negative 3. I have a point, I have a slope, so I can now use the point slope formula. And there we go, y equals minus 3x plus 1. Okay, so 9b is on first principles, using that formula to find the derivative.